Hello and welcome back to Bluehat Cybersec Academy. In this lesson, I am going to explain the following topics. First, asymmetric encryption, and second, symmetric encryption. These topics are part of Domain 5, Security Operations Concepts, in the Certified in Cybersecurity exam, and are useful for both exam preparation and for building a strong cybersecurity foundation. So, let's begin. Asymmetric encryption uses one key to encrypt and a different key to decrypt the input plaintext. This is in stark contrast to symmetric encryption, which uses the same key for both encryption and decryption. For most security professionals, the mathematics behind asymmetric encryption can be left to cryptanalysts and cryptographers. A user wishing to communicate using an asymmetric algorithm would first generate a key pair. To ensure the strength of the key generation process, this is usually done automatically by the cryptographic application or the public key infrastructure implementation without user involvement. One half of the key pair is kept secret and is known only to the key holder, called the private key. The other half, the public key, can be freely shared with anyone who wants a copy. Anyone can encrypt a message using the recipient's public key, but only the recipient with their private key can decrypt it. Asymmetric key cryptography solves the problem of key distribution by allowing a message to be sent securely across an untrusted medium without prior key exchange. It also provides additional features not readily available in symmetric cryptography, such as media, infographic highlighting non-repudiation, access control, and data integrity with digital checkmarks, motion graphic icons for digital signature, shield, and integrity non-repudiation of origin and delivery, access control, and data integrity. Asymmetric cryptography scales efficiently because each party only requires a key pair. For example, an organization with 100,000 employees would need only 200,000 keys, which is fewer than the number required for symmetric encryption. However, asymmetric cryptography is much slower than symmetric encryption, making it impractical for encrypting large amounts of data or for frequent transactions due to its mathematical complexity. Let's look at an example of asymmetric cryptography in action. The two keys, private and public, form a key pair and must be used together. Any message encrypted with a public key can only be decrypted with the corresponding private key. Similarly, a message signed with the sender's private key can only be verified by decrypting it with the sender's public key. If the sender encrypts a message using the recipient's public key, only the recipient with the private key can read the message, ensuring confidentiality. This method allows secure transmission over an untrusted channel. Symmetric encryption uses the same key for both encryption and decryption. In essence, the decryption process mirrors the encryption process. The main challenge with symmetric algorithms is that both parties must share the same key. While the key protects the data, it also introduces challenges. If the communication path is suspected to be compromised, sharing the key along that path is risky. Key distribution is difficult because sending the key along the same channel as the encrypted message exposes it to interception. Out-of-band key distribution, such as courier, fax, or phone, is necessary. Any party with the key can access or modify the message. Scalability is an issue, as the number of keys needed increases rapidly with more users. For example, 1,000 employees communicating securely with one another would require 499,500 unique keys. Primary uses of symmetric algorithms include encrypting bulk data, such as backups, hard drives, and portable media. They're also used for securing messages traversing communication channels, like IPsec or TLS. Plus, they help with streaming large-scale, time-sensitive data, including audio and video materials, and even gaming. Other terms for symmetric algorithms include same key, single key, shared key, secret key, and session key. An example of symmetric encryption is a substitution cipher, which replaces letters or bits in plaintext with other letters or bits based on a cryptographic variable. Each letter or bit is substituted according to a defined scheme, creating an encrypted message. This method demonstrates the basic principles of symmetric encryption in a simple, understandable way. That's all for now. Thanks for tuning in. Keep the momentum going by checking out the next video in the series. And if you haven't already, please like, share, and subscribe to Bluehat Cybersec Academy.